The title of this session is Cooking with Raspberry Pi, Connecting Sensors. And what I'm going to look at is a technique. This is quite specific really, but it's a technique for connecting sensors, analog sensors, to a Raspberry Pi. Because one of the things that the Raspberry Pi doesn't have, which the BeagleBone Black that we were talking about in the last session does have, is the Raspberry Pi doesn't have analog inputs. So there is a neat little trick you can do that just needs a few components, very cheap components, that allows you to use certain types of sensor called resistive sensors with a Raspberry Pi without having to buy difficult to use extra chips or add-on boards for your Raspberry Pi. So first of all, my name's Simon Monk, and I'm an author on the topic of Raspberry Pi, BeagleBone, and general electronics. The two books I have out at the moment relating to the Raspberry Pi are these two. Unfortunately, you may be able to find this one in the Maker Shed, but you won't be able to find this one in the Maker Shed. But they are available from all good booksellers, as they say. Okay, I'm going to be going through quite a few examples of code, and if you want to go home and try this out, then you'll probably want to go and fetch the code for yourselves. It's all available for free on GitHub, so if you have a look at these URLs, probably the only one you need to make a note of or remember is github.com/Simon Monk, and then you should be able to find the code for my Raspberry Pi books on there fairly easily. Some of the examples that I'm working on here are taken from this book. They're slightly modified, but they're taken from the Raspberry Pi cookbook. Others are also available as a kit through Monk Makes. If you have a look at monkmakes.com, there are some kits available that include, there's a kit available that includes using some of these resistive sensors. And finally, there's also a blog post that details much the same as this presentation at drmonk.com, which is my blog. So various different sources for finding out how to try this out. So first of all, what do I mean by resistive sensors? Well, what I mean is a kind of sensor that's resistance varies with some physical property. So a very common one is called a photoresistor. And the more light that's shining on the photoresistor, the lower its resistance, so the more current can flow through it. Similarly, you have a device called a thermistor. And as the name would suggest, that's a resistor whose resistance changes depending on the temperature that the thermistor is at. If you're thinking about how you can sense position, say for example on a twiddling a knob, like on a volume control or something, then the type of control that can do that is called a variable resistor, or sometimes called a pot, short for potentiometer. And this allows you to, because we're going to be able to measure the resistance on the Raspberry Pi, we'll be able to work out the position that it's been turned to. You can also get more unusual and fun resistive sensors, so you can get things like strain gauges that determine how much they're being twisted, or you can get gas sensors that have a special layer on them that reacts when gas of a certain type. So you can get methane sensors, various different carbon monoxide sensors, various other types of gas. And these sensors are quite low cost. They're quite readily available because they're used in the manufacture of various different types of safety alarm that you can buy in the home. So the approach I'm going to be describing here can be used for any of these types of sensors. You can adapt it to work with any kind of sensor that works by a varying resistance depending on the thing it's trying to measure. So let's start off with a little bit of theory about how this works. And the trick that we're going to use relies on a component called a capacitor. And if you're not that up in electronics, you're not that interested in electronics, then you may not know what a capacitor is. But a capacitor, you can think of it in water terms a bit like a tank. So as you fill the tank up with water or with charge, in the case of a capacitor, the voltage or the level of the water increases as it gets fuller. And the rate at which it fills up will depend on the resistance of the thing it's filling up with. So let's, but to be able to measure how long it takes to fill up, what we first need to be able to do is completely empty the bucket. So this is in fact the first step. We have a capacitor that's a bit like a tank, and then you can see we've got a drain valve on the bottom, so we can let any charge or water in there that's that's in the tank out, so that it's completely empty before we start measuring how long it takes to fill up. Okay, so then the next step is we close off the drain valve so that it won't empty again by any other means, and then we allow the capacitor to start charging up through our resistor. So if our resistor is a photoresistor and its resistance is very low when things are very bright, then charge will be able to flow through it quickly. It will have low resistance, so lots of charge will flow through, and the capacitor will get full, the tank will get full of water much more quickly than if it's really dark and the resistance is very high and is restricting the flow. Okay, so what we're going to do when we come and look at the program a bit later on is we're going to time how long it takes for the level of charge to increase, the voltage to increase in the capacitor above a certain threshold. So the second step is first step is we discharge the capacitor so it's empty, then we start a timer, and then we let the capacitor start charging up through our resistor sensor. And then finally, when it's half full, because with a digital input on a Raspberry Pi, you can't read a voltage, but you can tell whether a voltage is above or below halfway on a digital input. So if it's below halfway, it counts as a 0. If it's above halfway, it counts as a 1. So we can use the trick of knowing when it flips over to actually stop timing and say, aha, we know the tank's half full now, so we can work out what the resistance is. So if we now switch over from thinking about water in tanks and charging up through resistors, let's have a look at how that works in electronics. So you can see here the squiggly lines are resistors, and the two parallel lines labelled C, that's the capacitor. So what's going to happen is that we start by needing to discharge the capacitor so it's empty before we do anything else. So what we do is we say to pin A of the Raspberry Pi, which is, we say be an input. And because it's an input, it takes no real part that we need to worry about in the electrical system. Okay, it won't have any effect charging or discharging the capacitor because point A is acting as an input. We then set point B to be an output and to be low, to be 0 volts. And what will then happen is that the capacitor will discharge through RD, and basically all the charge will be taken out of the capacitor. When we've done that, we then make B an input so that the discharging stops, so that we're not fighting with the tank leaking at the same time as we're charging it up. So we do that by setting B to be an input so that B no longer takes any part in the process. And then we set A to be an output and to be high, to be 3.3 volts, the high output voltage of an Arduino, of a Raspberry Pi output pin. At that point, what happens is that current starts flowing through A, through RC, which is a fixed value resistor, which is just there to make sure not too much current flows out of the Raspberry Pi output pin. It flows through our test resistor, which is RT, which might be our photoresistor or our thermistor or our strain gauge or some kind of resistive sensor, and then it charges up C. And because in the meantime we've made B an input, we can keep monitoring pin B until such time as it flips over from being a 1 to a 0, and then we stop and we've got an amount of time. And we know that the resistance is roughly proportional to how long it took for the capacitor to charge up halfway. So let's actually try that out with a real example. So this is using a Raspberry Pi with some solderless breadboard. This is solderless breadboard, and it's a great way of prototyping circuits with the Raspberry Pi because you can just connect jumper wires from your Raspberry Pi GPIO leads onto the breadboard, the solderless breadboard. They just poke in, and then you can poke additional components into the board like this. So this layout here is the same as the layout you see on the screen. So let's start off with an example where we use a variable resistor. That's a resistor with a knob. And I should see how we can use that to measure resistance. So what I'm going to do now is switch over to the code, and if we go to where's it gone? Screen sharing. What I'm doing now is I've got the Raspberry Pi screen being shared on my laptop screen so that we can see it working. And this is the command line prompt. And I'm going to run a test program that's going to display the resistance of this knob here. So to do that, we need to do sudo. And the program is written in Python. .py. So there we go. That's showing us a value of resistance. The resistor is a 10k ohm resistor, so that would indicate it's about halfway. So if we could just switch over to showing the desktop. Control desk, would you mind switching over to the... Thank you. Oh, sorry, I do it, don't I? Beg your pardon. Okay, there we go. Right, so if I switch this back to right up to one way, and then I put it back to my Mac. Okay, we see that saying 10k ohm. And if I switch it all the way back the other way, unfortunately you can't see this varying as I turn it. I only see one thing at a time, so switch back over to my Mac, and you see there we've got a reading of pretty much 0 for the resistive sensor. Okay. So let's jump back and have a look at the code that you have to write to be able to do this. Let's go over here, back to the presentation. Okay, so at the beginning of and as I said, you can fetch all this code from GitHub. So don't worry about taking notes or taking photographs. You can get it all from GitHub and try it out. The first thing we do is import the library Takinta, which is going to provide the graphics for the project. We don't need to worry too much about that. We're more interested really in how we get the resistance value. A couple more libraries we need to import. rpi.gpio, which is the library used to control the GPIO pins. And then we also import time and math, because we're going to be doing a bit of mathematics, and we also need to be able to time how long it takes to fill the capacitor up to halfway. The GPIO.set mode sets the mode for the GPIO pin names to be the Broadcom mode. There's unfortunately two conventions for how you refer to which of the pins on the Raspberry Pi that you're using. So we're using the convention BCM in this example. We then define two pins, the A pin and the B pin. And the A pin and the B pin just refer to the pins I was talking about earlier when we were going through logically how this whole process of using a resistive sensor works. So what we've got here is most of the rest of the code. So if we look at the first function we've got here that's called analog read, it really does two things. It first of all calls a function discharge that's going to empty our capacitor, and then it's going to return a value that is the result of calling the function charge time. And the function charge time is what's going to time how long it takes for the capacitor to get half full. So first of all, discharge, what it does is set pin A to be an input so that this top part of the circuit has no effect anymore. There's going to be no charging through the test resistor. Nothing's going to happen with A. It then sets B to be an output, so this pin is going to do something, and it's going to set the output to false, to be 0 volts. So point B will now be 0 volts, and the capacitor will discharge through RD until it's pretty much empty. We don't actually test to see if it's empty because we don't have a way of doing that. We can only tell whether it's above or below a threshold of halfway. So we just do it for a certain amount of time. So in this case, for a tenth of a second, we just allow it to discharge. We then have the function charge time, and this is the thing that is actually going to measure the amount of time taken for it to charge up halfway. So the first thing it does is set pin B to be an input, so that we can forget about this part of the circuit now. We're just going to be concentrating on how the capacitor charges up. There's going to be no discharging while it's charging. So that's setting B to be an input. We then set A to be an output, and we also set A to be true, to be high. So this will now be 3 volts, and that voltage will have to pass through the fixed capacitor RC, and also RT, and RT is our test resistor, our variable resistor. So in this case, this variable resistor, in other circumstances, a photoresistor or some other type of resistive sensor. And what happens once it's set the output pin A to be high so that it's charging the capacitor, the next thing we need to do is set the variable T1 to be the current time, the current number of, I think it's microseconds, okay? And then we need to just wait and do nothing until the input has gone high, okay? So until the input B has increased above its threshold level, we just wait. So as soon as it's above its level, we then record a second time, and then we just return a difference between the two times, multiplied by 1,000,000 to make it microseconds. Okay. The next part of the code just actually turns that amount of time into an approximation of the resistance. And because the whole thing tends to work, there's timing jitters and other things, what I actually do is take 20 readings and average them. And then do a little bit of maths on the readings to calculate a value for the resistance. And then finally that returns the resistance as well. Okay. Okay, and the rest of the code example is all just to do with the user interface. So we have a class called app that's part of the TK that is used to allow the tkinter graphics library to be able to display a field. So we've got a field here which is a label with a label of resistance, and it's got that's just a dumb label to say this is the resistance. And then underneath that we've got we have another label that we're going to use to display the value in. And we do things like set the font of that, so it's a Helvetica 110 points, so it's nice and big and we can see what we've got. And then we just call a function called update reading. And what update reading does is read the resistance, and then it just does a bit of scaling on that to actually give us back and fit it into one decimal place, and then that displays a value of resistance for us. And then finally it sets a timer to call itself after half a second, so that the reading will be continuously updated. As we turn the knob, the reading will continuously change. And then the very, very last piece of code just opens up the window and gets everything running. So as I said, this code available from GitHub. Take a look at it. So if we wanted to measure light instead of measuring position with this, then it's fairly easy. We can just swap out our variable resistor for a light-dependent resistor or a photoresistor. So if we could, I can do that, can't I? Just switch over for a moment to the board so you can see what I'm doing. So I've taken the variable resistor out, and I'm just going to pop in this device, which is a photoresistor. So it's just a little component with a clear top, and there's like a sort of zigzag line on it, and its resistance will vary depending on how much light is falling on it. So again, let's run up a little test program to do that. We'll close this program, and then we'll run lightmeter.py. Okay, so this time it's giving us a reading of the light intensity, and if we cover it up, we should see that light intensity decreases. We take our hand away. Sorry, you can't see that, can you? Let me just put it back to this button. Okay, so there we've got a reading. I put my hand over the light sensor, and then the reading decreases. Take my hand away, and the light reading comes back up again. Okay, so the code for doing that is, let's go back to here. Yeah, so the code for doing that is actually, most of the code is identical to the other code we're using. We're still going to work out the resistance, and then once we've got the resistance, we then have another little function that just does a bit of maths on that to give us some kind of reading of the light level. Light is usually measured in a logarithmic scale, so that's why we take the log of it to give us a reading. Final demonstration, measuring temperature. So this time I'm going to use this thing here, which is a little thermistor, and take out the light sensor, pop the thermistor in. Okay, there we go. And if we run the test program for that. Put that back up onto the monitor. Okay, so there we've got a reading of temperature, and if we squeeze the sensor between our fingers to get it warmed up a bit, see the temperature gradually rising. Feels a bit hotter than that in here today. I'm not sure quite how accurate that is. I don't know if anybody else thinks it's warmer than that. And then we let go of it, and the temperature will gradually drift back down. You get the odd spurious reading. I think that's probably loose connections on this board here. Okay, so we'll just have a quick look at the code for the temperature, because that is slightly different. The bulk of it, measuring the resistance, is just the same, but there's a few little refinements to be able to calculate the actual temperature. And the main difference is this temperature from R, temperature from resistance function. And the way thermistors work is that they have a very well-defined formula for calculating the temperature. So they have when you buy a thermistor, it'll have a constant called beta, that I've called capital B here, which is 3,800 for this particular thermistor. And the thermistor, when you buy it, will also have another parameter called the R0, and that's the resistance at 25 degrees C of the thermistor. For this one, that happens to be 1,000 ohms, so again, that's another constant I need to put into the code that suit the particular thermistor that I'm using. The rest of the code just stays exactly the same, so there's some maths goes on here that eventually calculates a temperature. And I'm running a bit short of time, so I'm not going to go through that, but have a look at if you look up thermistor on Wikipedia, there's a good explanation of how to calculate a temperature from the resistance of it. Okay, so to summarize, you don't necessarily need to buy an analog to digital converter chip and extra hardware to use sensors with the Raspberry Pi. Even though it doesn't have analog inputs, you can use this trick with a digital input to be able to measure resistance. The accuracy isn't that great. That's one thing to bear in mind. If you're looking for very high resolution, high quality readings from sensors, then you probably need to use proper analog to digital conversion hardware rather than this approach. For example, the little capacitor on here, when you buy a capacitor, they typically have a tolerance of 10%. So it could be plus or minus 10% of its stated value. So that's right away introducing an error into your system. So you can calibrate that. Once you know which capacitor you're using, you can kind of take account for that, but not terribly accurate, but good kind of sensors where you just want to get a rough idea, or it's a one-off project and you don't mind putting in the time to calibrate it accurately. Okay, so for further information, you can find me. I'm here all weekend over at the Tab Book store. Well, Tab Book stand, I should say. It's not a store, we're not able to sell the books. And that's about 2 blocks over that way towards the main door, almost directly behind this stage. You can find out more about my books and my various projects and my blog on www.simonmonk.org. And you can also follow me on Twitter, where I'm SimonMonk2. And as I said a few times, all the code for this is available on GitHub in my repository.